Hello, everybody. Hey, we are back with a little lecture on graphing of the kinematic equations, which is going to describe a lot of our motions here. And it's important that you guys learn how to interpret graphs to actual movement and movement to graphs. The question of the day today is about an airplane coming in for a landing, okay? And then tomorrow's question of the day is the same question, but what I want you to do is to graph the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. On Thursday, you're going to have another situation, and at the end, you're going to end up sketching all these graphs as well. So I'm going to go over and talk about what these graphs are going to look like for their motion and situations in which how they relate to each other. So I am giving this lecture second period on Tuesday, and so we have a student in class, so I'm going to probably be directing my questions towards her. So hang tight here and follow along. You're going to take notes, and you are going to then submit those notes when I put this in as a lecture. All right. So whenever we have something that moves or doesn't move, we can graph where it is. And we talked about this last week, particularly when we talked about average velocity and whatnot. And one of that situation is if we have a situation like this and we have something like that, what is that describing?
It's standing still.
Okay, standing still at 4, right? And just right here, we would have something standing still at -1. Okay, we're all good. So now, and again, we talked about this before, okay? Well, what if we had something like this, and let's do, I don't know, let's go 1 and 2. Okay, so what is this describing?
Like it's like speed.
Say it again.
It's speed.
It's speed, and how do we know the speed? How do we know the speed looking at that?
You like the position over time.
It's position over time, and so if we, for example, connect to this point right here, how would we calculate the velocity?
You would do like the position over time.
Right, and so we're going to have the rise over the run, okay, which is going to be 4/2, which would be meters per second, which would be 2 meters per second, okay, and remember, that's just the slope. That's just the slope. Okay, now, if we had something like that, what is the slope of this line? Okay, that's going to be 2 as well because they're parallel. So what's the difference between them? It's just where they're started. So we could also have one like that, right? So we could have 3 people starting, for example, a race, and they're all going to, at this point, they're going to be 1 meter apart, but they're all going to be going in the same speed, okay? And again, that was a bit of a review from last time. And now, if we wanted to graph this on our position versus time graph, and we're going to say 1, 2, 3, 4. Okay, I'm going to get rid of this for now. What would this graph look like?
Would it be like a straight line?
It's going to be a straight line, and it's going to be right like that. Okay, where it's going 2 meters per second. So a straight diagonal line on a position versus time graph is going to be a straight horizontal line on a velocity versus time graph. And now if we go over to here for an acceleration graph, what is the acceleration of that object? Okay, you want to say 0, and you are correct. Okay, so this is going to have 0 velocity because this is telling you it's a constant velocity. And this, so we're going to go a straight diagonal line here, which is going to be a horizontal line here, which is going to give you a straight line, but at 0, on that line. Okay. So now, if we had a line like this, if we had a line like that, okay, what would the velocity of this line be? It'd be the same 2 meters per second, but since it's going down, it's going to be negative. And then if we're going to have this one right here. You guys, blue seat, and we're just recording and taking notes on graphs of position and velocity and acceleration. And you guys will catch up pretty quick. Okay, and so this line right here is going to go here, but what is the acceleration line going to look like?
Is it the same?
It's going to be the same, right? Just because it's 0, Okay, so now what I'm going to do here is we're going to talk about an acceleration. What does the graph look like if we have an object that is not 0 acceleration? And again, we talked about this last week in one of the lectures without really graphing it so much. Okay. Now, what we're gonna do here is we're gonna have something like this. We're gonna have something like that. Okay. And again, we are sketching this, so my numbers might not be, or my graphs might not be specific to this, but remember, this right here is a sloperometer, okay? So that means this kind of gives us a quick indication of what is going on here. For example, right here, the slope of that is obviously 2 that we figured out earlier, and then that would be -2. Again, this is rise over run. Okay, so now at a certain point right here, like even going at 0, let's just assume that the slope here is 0 at 0, okay? And as we progress forward, this line is getting steeper and steeper and steeper and steeper. And then right up here, okay, and again, if we wanted to calculate from the graph what the velocity was, is we would take a point on there and then get its tangent line, okay? So this line right here is roughly tangent to that black line right there. And then what we could do here is give it a one like here. So the rise is approximately 40 and the run is approximately 10. And in this case, centimeters. So we're really just 4 and 1 from these graphs right here. Okay, so right there, we're going to have a slope of 4. Right here, we had a slope of 0. And even though it might not quite be correct, okay, we're going to say we've got a slope right here that is a slope of 2. Okay, so what we've got here is something that is accelerating. So we can see that it is changing. It is changing its velocity over time. Okay, so now we are going to start out, when we take this black graph, this accelerating graph, okay, and it is changing, okay, it's starting at 0, and then let's go 1 second, and 2 seconds. And at 1 second, we've got a velocity of 2. And at 2 seconds, we have a velocity of 4. Does that make sense? Okay, so now we can connect these, and I am going to adjust my little line here. So that is 1. This is going to correspond to here. So what we get here in these kinematic graphs here, if we have a curved line like this, okay, that's going to be acceleration, okay? And if this is parabolic, okay, if that is parabolic, okay, then this right here is going to be a straight line, okay? And you guys, we're really going to when we talk about graphs, I'm not going to give you something that is not parabolic, okay? And so it's always going to be, and if we kind of go back, distance or position is equal to VIT plus 1/2 AT squared. So if we remember this equation from last week, and I might have had this X, and I might have had this as delta X, okay? So this equation right here, we can see is a quadratic equation, which is going to give us a parabola, right? So that parabola, right here is going to be one side of that parabola, a quadratic, if you would. So when we have a quadratic in the position versus time graph, we're going to have a straight diagonal line on the velocity versus time. And then if we look here, what is the slope? What is the slope of this line? It is 2, because we're going to go up 4 over 2, except this is not 2 meters per second squared, okay? The rise is 4 meters per second, and the run is 2 seconds, and that is going to give us 2 meters per second, which is going to give us 2 meters per second squared. 2 meters per second squared. So we can see here, now it just so happens to be that they have the same number. They have the same number, but they're not the same graph, okay? They have the same number, but they do not have the same graph, okay? All right, so if we take and we want to graph this velocity versus time vector here, okay, this line here, and we want to graph it on an acceleration versus time graph, what is it going to look like?
A straight line.
It's going to be a straight line, and it's going to be a straight horizontal line, and it's going to be a straight horizontal line at 2. Okay, and that is going to be like that. Okay, pretty straightforward. Okay, so now, you guys, I'm going to give you situations over, this week and even right now, of some situations that you're going to have to interpret. You're going to have to interpret what's going on. And for example, tomorrow's question of the day, you have the airplane landing on a small airport on an island. So you're going to do all the math here. This maybe being one of those questions that you're going to use, the 4 kinematic equations. But then tomorrow's question of the day is you're going to sketch out these graphs. You're going to sketch out these graphs right here for today's question of the day. On Thursday, whole separate question. There's actually going to be 2 things that you're going to do, and then you're going to sketch out the graphs, position, velocity, and acceleration. And you are going to end up on Thursdays, you're going to end up having 2 lines for the 2 situations on these 3 graphs. Okay, so I'm going to I'm going to kind of get rid of the, well, now I'll go red here and we can see. What if we have a situation, let's say, like this. So if we have this red line, okay, if we have this red line that's curving down like that, what is that line representing? What is that line representing?
Its position is like decreasing.
The line is decreasing. Okay, where is it starting?
At 4.
Starting at 4. How fast is it going at 4? How fast is it going at 4?
So 4.
Okay, and let me change this to make it a little more obvious. Okay, so you guys, what is the slope? What is the slope of that line at 0?
It's 0.
It's 0, right? So we're starting out in this one right here. We're starting right here with a velocity of 0. We're starting with a velocity of 0. Okay, again, let's take it at 1. And if this is the same graph, just a different orientation, and at 1 second, what is the slope of that line right there? -2. Okay, sorry, -2. Okay, so now at 1 second we are at 1 second we're at -2, and then if we get here, and again, assuming that it is symmetrical with that one, we're going to have -4. Okay, and so we're going to have approximately this line right there. That makes sense? Okay, so I think the key to understanding these graphs, even if you're going in the reverse, okay, is take a look at your sloperometer. Take a look at your sloperometer. Okay, and if we look here, and we're going to go and get the graph there, we're going to have an acceleration of -2 there, because our slope on our velocity versus time graph is going to be equal to -2. Okay, you guys, this right here should give us all kind of an idea of what's going on from a position, velocity, and acceleration versus time. You guys, I'm going to give you guys some more practice with this when it comes to sketching out these graphs, or probably the question of the day on Friday is I'm gonna give you the graphs, and then you're gonna give me the information from a problem. Okay. All right. So this is it for this lecture, and what I would like you guys to do is just I'm going to have a spot for this in class or in your week 2 materials, and you're just going to give me a picture of your notes, and that's going to give you credit.